All right, so we'll go ahead and move on to the next talk in this session, which will be William Farrell talking about mapping the surface potential and ion flow in the lunar south polar region.
All right, can you hear me okay?
Yep, I can hear you.
Can you hear me okay?
Yes, I can hear you at least.
Okay, great. And you can see me, and you can see my screen, right?
I see your screen, yep.
Great, let me get this, yep, hold on, it should be. There we go, sorry about that. What I'm gonna do is give a little review over really almost 10 years of work on our work on mapping the surface potentials in the lunar polar region. And the reason why this is important is because, of course, ion inflow and the surface potentials have a lot to do with weathering, but it's also, these maps can give an indication of where you have to look out for anomalous charging to explore. So there's both an exploration and a basic science reason for looking at this study. I'm going to also emphasize some work recently by my colleague, postdoc Doug Rhodes, who's actually left Goddard in February. So he has some new work on this, which I'll highlight as well. So as you know, the moon spends 3/4 of its lunation immersed in the solar wind plasma. And of course, this talk is very different from Carly, who's talking about solid rock stuff. I'm talking about plasma, the most ethereal, low density. In fact, at 1 astronomical unit out near the moon and the Earth, the solar wind is 5 particles per cc. Of course, it's streaming at 400 kilometers a second. In fact, it's the flow, the plasma flow, which consists of protons and electrons, is collisionless. But the particles do exert an influence on each other. You can almost think of it as a viscosity through their electrical forces. For example, if you displaced a set of electrons relative to the ions, there'll be an electric field that will draw those electrons on back. And of course, the moon, which is mostly non-magnetic, it represents an obstacle, a solid surface obstacle to this plasma flow. And there's actually a trailing wake, which actually ends up being part of, which we'll talk more about. So, so if you just looked at how the surface of the moon would charge without any topography, because really the regolith is an insulator, it's really a story of contrast. On the day side of the moon, solar radiation frees up photoelectrons, and the surface charges a few volts positive. However, in the night side, you have this lunar wake. Really, it starts out almost as a perfect void that goes out to 10 lunar radii, and the density drops out to about 1/500th of what it would be in the solar wind. Further, on the night side, the surface charges up strongly negative. So it's a few volts positive on the day side, strongly negative on the night side, and you have this steep transition region up near the terminator. So the terminator is very complex. And just to show you that some of this is backed up by data, we have some superthermal ion detection experiment side LSEP data, which actually shows this drop in the surface potential as you approach the lunar terminator from near zero to minus 100 volts here up near the terminator region. One of the things we started looking at then, barely inspired by the side data, is exactly how the solar wind would flow in the polar region. You have to realize that the solar wind is flowing horizontally in the polar region, and things like mountains and craters represent obstructions to the flow. And what you're going to form are little mini wakes behind the mountains and the craters, giving rise to large variations in the surface potential at the regional and local level. So we examined this plasma flow and expansion process. I mean, what really happens is the plasma flows over, gets obstructed, but the electrons move in ahead of the ions, and you end up with an ambipolar or an expansion electric field, which then deflects the ions in behind the crater. So it just doesn't stay a perfect vacuum behind these objects. The electrical forces actually, in some sense, deflect the ions, actually, in real sense, deflects the ions into the crater. So we modeled this effect. We modified known plasma expansion equations, and now included the fact that which were normally one-dimensional, we include the fact now that they're both flowing in one direction in delta X and expanding in delta Z. Right, and this was in 2010, we looked at this. And a great example of this that we did is we looked at the plasma potential that forms within Shoemaker crater. Now, of course, this is a model, and early on we were using the Goldstone radar topo data, but when you get our plasma potentials, you can almost think of it as almost like on Earth, they'd be comparable to pressure systems in weather. So this is space weather within Shoemaker crater, but it's in the form of electrostatic weather. And the plasma potential goes strongly negative on the leeward side of the solar wind flow, primarily because that side is in need of getting some ions, so it charges strongly negative on that leeward side. On the far side, ions are deflected and surface is less negative. One big, and again, that these negative surface potentials are indicative of regions where you have a plasma dropout. In fact, the plasma density drops out as the exponential of the potential divided by the electron temperature. So in the leeward edge, you're getting a plasma dropout of almost over 1,000. Now, given this kind of model, you can now make surface potential maps. And these maps included both the expansion potential and the near surface sheath surface potential that forms. And actually, the maps look stunningly like illumination maps, don't they? Well, of course, they kind of should, because where you're getting the sun illuminated, that's where you're releasing photoelectrons and your potentials are a few volts positive. In contrast, where it's in shadow, you're getting that plasma expansion effect and the large negative potentials. So in fact, we ran our codes and end up with these maps. This is for solar wind flowing, I think for third quarter and for first quarter moon here. Given these models, you can do other things, like you can adjust the plasma temperature. For example, in the middle here, you have the typical solar wind of 10 electron volts. In plasma, we talk about temperatures in terms of electron volts. Each electron volt is 11,600 degrees Kelvin. So you're talking about 100,000 degrees Kelvin for the plasma, right? Not the surface, the plasma. Really represents the width of the distribution. But what happens is when a solar storm, a coronal mass ejection, is emitted from the sun, right behind it, you form a shock, but right after the shock passes the moon, the plasma warms up. And of course, our models would suggest that as the plasma warms up, the surface potential goes more strongly negative, right? But then once that warm plasma leaves and you're getting to the driver gas of the coronal mass ejection, it's actually a cooler plasma. And so in that case, the plasma is less negative. So these kinds of maps and these kinds of models allow you to map the dynamics of the solar wind down to the south polar surface where our astronauts are going to be. So Dov Rhodes, our postdoc, again, he left in February. Otherwise, he probably should be presenting this, but I have a chance to present this. You can tell I did it because I think I spelled instantaneous right. Anyway, this is he ran these models, actually modified them and ran them for Shackleton crater, kind of updated the models. And you can see again in Shackleton, you can get on the leeward edge of the flow large negative potentials up in the upper left of minus 100 volts or so in that leeward edge, and you see the density. You see the density dropout on that leeward edge. Also, what you can see here in the lower left-hand panel is the ion flux, showing that the ions do in fact hit that far wall, but don't hit that leeward wall. So what you can do, okay, gotcha, a couple of 2 minutes. What he did then is a lunation integrated ion flux of the ions getting to some of the various polar craters. And this just came out in a Planetary Science Journal. But in particular, he found that, of course, there's a reduced ion flux to the floor of the polar craters on a lunation integrated map. And it's particularly true for Shackleton, probably due to the unusual or relatively higher depth to diameter ratio, which doesn't allow the ions to deflect in to the same degree as it would the larger polar craters. You can also look at things at Sputtering Lifetime for a 0.5 micron ice layer. And he found that on the walls of the craters, it's relatively short, like 100 years, but in the floor of the craters, because of the reduced ion flux, can be closer to 10,000 years. But notice we're not saying a billion years. In other words, even if you, by sublimation processes, can keep that ice on the surface for a billion years, sputtering and plasma inflow really will limit the amount of time that ice will stay surface exposed to, tens of thousands of years, sort of thing. Another application is charging. He has a paper out in Advances in Space Research on drill charging in a polar crater, where you generate charge by the triboelectric contact between the drill head and the regolith. But what happens is the regolith itself is a poor conductor in these cold regions, and you're in a plasma starved polar crater, so you run the possibility that you can develop anomalous charging on the drill. In fact, he was modeling it with over 10 kilovolts in a few seconds. So that's something that you got to think about and need sound engineering practices to figure out how to remediate that kind of charge buildup. And in his paper, he discusses a couple of these. So to conclude, we've got these predictive maps. Actually, we've sent them to Marshall Space Flight Center, who are using them as part of their space environment studies. But ultimately, we need a modern day landed plasma system to sort of validate and map out the potentials for real for comparison to our simulations and our modeling. But again, the applications include charging within the craters, near these obstructions, and actually ion influx and plasma sputtering into polar craters, where you as a loss for the volatiles, surface exposed volatiles. Anyway, that's it.
All right, thanks, Bill. There is one quick question. Do you think similar things will happen to topography shaded regions on the illuminated surface, such as shadows of crater walls? And how do you think this effect compares with direct solar illumination?
I'm not sure could you repeat the question?
Yeah, it says, do you think similar things will happen to topography shaded regions on the illuminated surface, such as the shadows of crater walls? How do you think this effect compares with direct solar illumination?
Yeah, it depends on how deep the shadow is, and roughly the term plasma folks use is a Debye length. And if you're many Debye lengths in the solar wind, the Debye length is about 15 meters. So if you are at the terminator and you have an obstruction that's a couple or three Debye lengths, you'll start to see these really strong changes in the plasma potential. Less than that, you'll probably get a reduced effect.
All right, great. Thanks again, Bill. I think there's some more questions in the chat that you can take a look at if you have time.